Great. Hey everyone, thank you for coming to my talk. My name is Abe Ratnofsky, and I've been working on Cassandra since 2021, and I've been a committer since earlier this year. Today I'm going to be talking about CEP 45, mutation tracking. This is a new feature that's in development, and we don't have a target release for it yet. My goal is to tell you all about mutation tracking and why you should be excited for the feature and not afraid of it. Cool. So we're going to break this down into three sections. I'm going to give a little bit of background on entropy in Cassandra, what that means. It's a very cosmic sounding term, so I want to make sure the reality is very clear. I'm going to talk about how existing anti-entropy can fall short, and offer mutation tracking as a better, faster, and stronger alternative to what currently exists. I also want to make sure to give credit to folks in the room and not in the room who put a lot of work into this. So Blake Eggleston, Alexei Yashchenko, Ariel Weisberg, and Caleb, who are mostly here. This has been a bunch of effort from a bunch of people, and I'm just the one presenting it. So first, let's do a background on entropy. What do I mean when I say entropy? So the basic issue is that a user can do a write, send it to a coordinator. Coordinator sends that to replicas. Not all replicas get it. Client gets an ACK back, because we met quorum, the consistency level is met, but nodes 1 and 2 agree, node 3 disagrees, client is happy, we're out of synchronization. So nodes 1 and 2 are good, but node 3 is missing something. And this is not an optional situation. This is, partitions will happen, messages will be dropped. Part of the goal of Cassandra is to tolerate that well. So this will happen. We don't have a way around it. The status of that synchronization isn't known until incremental repair runs. So it's only once we run incremental repair, we check what's on disk, we produce digests for what's on disk, we send those digests around, we send data around, and then we say all the data that was involved in that session is now repaired. And all of that work, all that going to disk, producing digests, stringing it around, it's expensive, but it also means that we don't run this. We may run it periodically, we may run it every hour, every 30 minutes or something, but it isn't running continuously. So there can be data that's fully in sync, but we still consider it unrepaired. Data synchronization, though, it's a huge part of correctness and performance. So if we purge unsynchronized tombstones, we could resurrect data. If we don't repair before we do a host replacement, we could lose writes. Repair-aware reads and backups only need one copy of the repaired set. So there's a lot of opportunity to improve efficiency by doing repair and keeping repaired and unrepaired data separate. And validation repair is our best tool for finding logical data corruption. So this Cassandra 19617 Byzantine critical bug from earlier this year or last year was around stale distribution of commits that were purgeable, and this broke validation repair. When we ran validation repair, we found that the repaired set on nodes disagreed because data was being distributed that shouldn't have been. So validation repair is our best tool for logical data corruption. We can't use things like checksums to figure out database bugs, besides database bugs that can be found by checksums. But if we're propagating the wrong data and that data has the right checksum, we need something like validation repair to find that logical corruption. So data synchronization is hugely important. It's not optional, and it needs to work well. I also want to give a big shout out here to the folks who worked on CEP 37, the unified repair solution, because a lot of this know-how and these sharp edges existed in recommendations before and are now much more mechanized into tools that people can use much more effectively. So I want to make sure that is known. That's really great and really helpful work for improving anti-entropy. So we have 4 main existing systems that do things that could be called anti-entropy in Cassandra. We have hints on coordinators when replicas don't respond to writes. We have read repair for during the course of a read, making sure all participants in that read have the most recent data, which we need for read monotonicity. And then we have full repair and incremental repair that take data that exists on disk, produces Merkle trees for them, produces digests for ranges, and then compares those digests to figure out what needs to be streamed where. All 4 of these, though, they do have sharp edges, and they can all be pretty expensive. So what if we could do this a whole lot better? What if instead of repairing partitions in full, we could reconcile individual mutations? So if you had a partition that was a gig, but mutations that were just a few bytes, what if instead of spreading that entire gigabyte partition around every time you had to stream it, you could just reconcile what was missing between two peers? What if instead of repairing periodically, like every hour or every day, we could reconcile continuously? So during the course of a write, or during the course of a read, we're actually making sure that nodes are converging on the data that exists. And what if instead of scanning user data from disk in order to produce digests, we could come up with reconciliation plans that were really compact, fixed size comparisons? So if users want to write a 1 megabyte blob, that whole blob doesn't need to be scanned in order to produce a digest to figure out whether or not it's in sync. What if we could do all of these things and provide even stronger guarantees and even better performance for operations outside of the main anti-entropy paths? So this is our goal. This is where we want to get to. Helps us with larger partitions, larger values, keeping the unrepaired set as small as we can, and with even stronger guarantees elsewhere too. So that's the anchor of everything we would like to achieve with mutation tracking. So now I want to talk more specifically about what that means. So mutation tracking, I'm calling it better, faster, stronger, because it's stronger guarantees, it's faster as in less work has to be done, and it's better in that it works for workloads where digest repair struggles. So larger partitions, higher replication factors, larger values. So instead of doing a write coordination and then later picking up the pieces to decide whether or not things are synchronized, tracking propagation continuously during write coordination lets us do a lot of work a lot earlier. We can also, if we're running during write coordination and read coordination, run continuously, keep a much smaller unrepaired set. We can also reduce the unit of repair from partitions, no less than a partition, and even smaller if we have truncated vertical trees, to a single mutation. So if two peers have large partitions but just disagree on a small amount of that, just send that small piece of data. We also want to eliminate hints and overstreaming. Hints which can consume a bunch of effort but provide no strong guarantees. And overstreaming, which can exacerbate issues like small divergence between partitions, meaning large amounts of data needing to be streamed across. We also want to offer stronger guarantees around write atomicity, read monotonicity, which are guarantees that users currently need to make a decision between in the case of read repair. You can either have read repair and break write atomicity by repairing only the section of a partition that's been read, or get read monotonicity and or lose read monotonicity by disabling read repair. So you have to make the decision between these two things, which can conflict. I've done a lot of promising of things, saying, look how great this would be. I also want to make really clear that this is an optional feature. So this is something that will not be forced on you as part of an upgrade. This is not a default that I'm saying, surprise, in Cassandra 9.0, you will be forced into this way of working. This is coming in as a new option. You'll have an opportunity to qualify it. You'll have an opportunity to reject it and say, you cannot use mutation tracking, we don't like it. It is totally piecemeal, and we'll support migrations as well with an alter key space state. So this is very pluggable is such an overused word, but this is something that you can safely disable and not feel like you're subscribing to if you don't feel confident in it. So now I'm going to talk about some more details on what mutation tracking really means. I'm going to talk through this more specifically because it's blurrier than I expected, but there are a few pieces of write coordination that now adjust if we're tracking individual mutations. So on the left, we have a client and then a coordinator and 3 nodes. This is the write path for a coordinated mutation. There are 2 pieces of it that are really different from the standard path. That's the assignment of a mutation ID in the beginning, and then the marking of the propagation of the ID at the end. But the middle is all familiar. That's the coordinator sending mutations to replicas, replicas acknowledging, meeting the consistency level, and acknowledging to the client. So I'm going to talk more about what assignment of a mutation ID means, and then what this marking is. So this mark ID1 at node 1, node 2, mark ID1 at all. I'll talk more about those two pieces because those are the new parts. So first, we want to assign mutation IDs. We want to give each mutation a little tag so that when we send it to the different nodes that own it, those know what they received. So the coordinator says, I'm now coordinating mutation ID 1, and when it sends it to node 1 receives mutation ID 1 and can mark down that it received mutation ID 1. So now everyone has a name for this thing that they're all working on. That ID is used to record reconciliation state on the coordinator, where it can then record, as it receives acknowledgements, where those acknowledgements came from. So by the end of this, right, actually, when we act back to the client, we've met quorum, 2 out of 2 responses received. We know that ID 1 is present at node 1 and node 2. Those nodes have acknowledged this mutation ID. And then when we receive the last one from node 3, we know that this mutation is reconciled. There's no more work to do. We don't need to go pick up the pieces from what's on disk. We know that that mutation is everywhere it needs to be. So in addition to doing what we would traditionally do of counting replica acknowledgements towards the consistency level, we're also tracking them towards reconciliation. So each mutation, we know where it's been acknowledged, and so we know where it's missing. And that lets us ask this new question that we've never been able to ask before, of which mutation IDs are present on each node. And these IDs are small. If we have a 1 megabyte mutation for writing bombs in the Cassandra, mutation IDs are still a fixed size. So we can ask these questions and get really compact responses of node 1 has these mutations, coordinator has coordinated these mutations and they propagated to these places. So now we have a new piece of metadata that we didn't have before. And that's available by piggybacking off of the right coordination maps. This is, I think, really exciting because right coordination already does so much of this work. We already get so close to saying, hey, this mutation is everywhere, you have nothing to reconcile. But now we're just doing a little bit more work on the same path instead of discarding all of the work we did to propagate a mutation and then picking up the mutations from disk later and saying, hey, I've got this thing and I'll assign this, I found this digest for it. So we get to piggyback off of the existing right coordination and get reconciliation state for very little marginal cost if we do it at the right coordination tool. So this is how rights work. We can now answer this question of which mutation IDs are present on each node. And with that, we can figure out what's necessary in order to do reconciliation. So if node 3 never actually acknowledged that right, we never got that app back, and the coordinator just thought that the ID was at nodes 1 and 2, we would know that node 3 needed some reconciliation. So now I'm going to talk a little bit more about what reconciliation plans look like. So we know which mutation IDs each node has. We know, this is a separate example, but let's say we know that node 1 has these IDs, it's just missing ID 4. We know node 2 has these IDs but is missing ID 5. We know node 3 has some other IDs but is missing ID 1. We can come up with a plan just based on the IDs. So we don't need to take a look at anything that's on disk. We don't need to compute any digests. We know based on the presence of IDs who has what and what needs to be sent where in order for everyone to have what they need. So in this case, this is just integer math. This is going through these lists, finding what's missing and what's present somewhere else, and then coming up with a plan of who needs to send what where. So in this case, we know that node 1 needs to send to node 2, ID 5, needs to send to node 3, ID 1, and node 2 needs to send to node 1, ID 4. And if we do all that, everyone will have everything. We don't need to produce a digest. We don't need to scan things on disk. We know that everyone will have had all the mutations, and because mutations can be applied out of order, we know everyone will be at the same correct state. So producing this plan, one, is a lot cheaper than producing a Merkle tree. Everything is compact. All these are in memory, and it's not dependent on the size of the data on disk. And in order to do this, we need a way to send individual mutations from, in this case, from node 1 to node 2. We need a way to just send mutation ID 5. We know we can't do this out of the mem table. We can't ask the mem table for a specific mutation because maybe that mutation was overwritten and doesn't exist in its former form anymore. So we need a new thing to let us seek and find what the mutation is for ID5. That's a new idea. So now I'm going to talk some more about these new pieces of machinery that we need in order to do these really precise both accounting of mutation IDs and really precise reconciliations where we only send what's missing. So we have two new pieces here. One is a coordinator log, which is an in-memory index of local IDs by token. This is not mutations. This is just a collection of IDs organized by token on a replica, where that replica can then say which IDs it has present locally. This is used in reads and in reconciliation. And then we have the mutation journal, which Alex talked about just before this. This should be thought of a lot like a commit log, except it offers one additional really useful feature of looking up the content of a mutation by its ID. So it's appendable, but we can also seek and say, hey, for ID5, go fetch that and give me just what that mutation is. So that's how we answer that question from the previous slide of how do we get that ID to send to a node that's missing. It's out of the mutation journal. And then we have the LSM, the log structured merge tree, the mem table and SS tables. And this is all faithful. This doesn't change. This is where reads need to go. This is where the rows come from. So we have two new pieces of machinery that are present on the local write path and as part of reconciliation in order for us to do this continuous, really precise version of repair. So I know I've mentioned this ID a lot, and I want to make that a little bit more concrete. So we know that we need to assign these IDs so that peers can determine whether or not they have the same thing. But let me be more clear about what that means specifically. So an ID has 4 parts, and these are assigned by a coordinator at coordination time. So when a user runs a CQL insert statement, we, on the coordinator, then take that, convert it into a mutation, and produce an ID for it. That isn't dependent on the content of the mutation, besides its token in some niche ways, but is based on the coordinator state. So the coordinator, it has a host ID that comes from TCM, that's just an int. It has something called a log ID, which is a basically a generation for that log to make sure that we never assign a duplicate ID in case we crash. So if we crash and restart, we will increment the log ID durably and then start up with a new log ID to make sure we're never reassigning assigning an old mutation ID again. And then we have a sequence ID, which is just an atomic increment, doesn't need to go to disk anymore because we have this crash protection in the log ID, and then an optional timestamp that we just included for debugging because we think it would be helpful. So when a coordinator needs to assign a new mutation ID, all it needs to do is an atomic increment and a clock read, and then it can fill out these 4 fields. And then whenever we start up and run out of sequence IDs for log ID, we'll do a durable increment to the log ID and make sure the new one is committed to disk so that next time we start up, we don't forget about it. So every time we start up, we get a new log ID, and that way we won't have any conflicts. This format of ID is also designed to be really compact when we have a lot of sequential IDs. So this offsets representation is a compact representation of a collection of IDs. So this is 1 through 8 and 10 through 15 and 16, where those are all the sequence IDs within a host ID log ID. So host ID log ID will change really infrequently, and then we can represent all of these offsets really compactly. So that is a ton, whatever, 15, I don't know, quick math. 15 mutation IDs approximately in that really compact representation. So that's what I mean by a mutation ID. We assign this new essentially sequence number to every mutation as we're coordinating. So that is we've done the write path, we've done how reconciliation plans are calculated. Now I'm going to go into what reads look like. So as a recap, we have 2 new pieces of machinery, 2 new things we can do. One is fetch this ID summary, which is all of the mutation IDs that have been applied on a replica in that compact representation. So we can fetch this ID summary from a replica by token, and we can fetch the content of an individual mutation by its ID. Those are our two new things that we need for reconciliation and that we track at write time. We can also, as we always could, read from the LSM, from the log-structured merge tree, and read rows. So these are our options, ingredients for what to work with. And we want to make sure that we can serve reads effectively, meet our goals with these three ingredients. So the first way to approach this, the first way to think about it, is to just do the reads like they were always done. Just read from the LSM and read from however many replicas you need, take those, merge the results, and then tell the client the merged results. This is 2 full reads, as is fairly normal if digest mismatch, and is the typical current path. Where this doesn't work, though, for mutation tracking, is read repair. In order to get monotonic reads, we want to make sure that all of the participants in a read received any mutations they were missing in the course of a read. So if we read from the LSM and we do something that looks like read repair and then send new mutations to replicas during the read, we're going to be doing a read but coming up with new mutation IDs to send to the replicas. And that doesn't really make sense. We're doing a read, no new writes are entering the system. Why would we be creating new mutation IDs and sharing brand new mutations to replicas? So that leads us to our better path for doing reads, where instead of reading from the LSM, we leverage these mutation summaries and use those as the input to what we call read reconciliation instead of read repair, instead of actually merging through all the results. So we know we need read monotonicity, and we're going to use summaries to produce that read monotonicity instead. So the coordinator, when it's executing a read, can do 2 different types of read. One is the standard, give me the rows from the LSM. It's not really rows, it's got tombstones included, it's an unfiltered technically, but give me everything that you would give for a normal read. That's this data from the LSM read. But we have a new kind of read too, which is this ID summary. And that summary is all of the unreconciled mutation IDs for a token or for a range of tokens, whether it's a single partition read or a range read, from the coordinator log. So we can get rows from a replica, or we can get these unreconciled IDs. And we can achieve the same semantics as traditional reads by reading once from one node from the LSM, so getting all the rows like a normal read, and then doing a fetch on that node for all of the unreconciled IDs it's aware of, and from another node, this ID summary. So in this case, we have one response of data from node 1, this rows plus summary, and we have one just summary from node 2. And remember, the summary comes out of memory. It's persisted to disk, but it doesn't need to be read off of disk in order to serve a read. And we have 2 of those, and then 1 of this data read. And I'm going to tell you about how this actually offers the same semantics as a quorum read otherwise would. So in this case, this is the happiest of happy paths. Let's say the summaries match. So the euphoric path, the transcendent, beautiful path. Nodes 1 and 2 have the same summaries. So they have the same unreconciled data on them. There's no disagreement. The coordinator says, you 2 have the same summaries. Great. In this case, if they have the same summaries, that means their unreconciled data is the same. And due to invariance, we know their reconciled data is the same. So it doesn't matter if we would do the read from node 1 or node 2. It should be the same data. So we don't need to read anything from disk on node 2. We can just say, well, we checked that the summaries match up, and send that read of rows that we got from node 1, send it to the client directly. That's great. That's a really wonderful scenario, because it means even at RF3, where we would do 2 reads, we're just doing 1. So we get the same consistency for half the cost. And you can think about this a little bit like a digest read. We'll do a digest read, and then we'll compare if the digest from node 2 matches the digest from node 1. And if they do, great, we don't need to do a data read from node 2. But the difference here is if the summaries don't match, and if the digests would be totally different, then node 2 basically needs to do its read again. It needs to fetch all of those rows again and send them back to the coordinator. So in this case, if the summaries mismatch, we actually have really useful information. We know what's missing from everywhere because we can compare these summaries. We can produce the reconciliation plan I showed earlier and know what needs to be put where, essentially. The other benefit of this over the digest read is that node 2 can serve this summary read out of memory. It doesn't need to go to an LSN and produce its unfiltered and then collapse it into a digest. It just needs to go to memory, find which of these IDs it's missing, and share that compact summary representation back to the coordinator. So it doesn't even need to go to disk. So we're saving on both disk and network over digest, where we would just be saving on network. So this is an extremely happy path. So obviously it's great. I'll get into some of the slightly less happy paths and show that they're still pretty happy. Okay. So what if the summaries don't match? What if node 1 says, the coordinator fetches some data from node 1, fetches the data and summary from node 1, and then fetches the summary from node 2, and then does the math for the reconciliation plan, compares the summaries, and sees actually nodes 1 and 2 disagree a lot. They don't have all the same stuff in their summary, so we need to find a way to proceed with this read. And this is going to be a relatively common case, especially if you have concurrent reads and writes. There will be some mismatch in the unreconciled set between nodes, and that's fine. What we need to do in this case are two important things. One is the coordinator has all this data from node 1 that is incomplete. It's missing some mutations from node 2, and it needs to make sure that those mutations from node 2 are present before it's sent back to the client. So we call that augmentation. The coordinator tells node 2 to tell it everything that it should also tell node 1. So if node 1 is missing something, coordinator is missing it too in that read response. And so node 2 needs to share to both of them, here are these missing mutations. And like from earlier, those mutations are fetched out of the mutation journal just by their ID. So if one mutation is missing, just that one mutation is sent. So the coordinator does its augmentation. It adds what it needs to what it's going to send back to the client. And node 1 gets what it was missing for read monotonicity. Node 2 also needs to receive everything it was missing from node 1. And so once everyone has what they need from what they were missing after preparing their summaries, we know we can respond back to the client and know that read monotonicity is maintained, and the response payload, the rows, are correct. So that's one unhappy path. And the magnitude of this unhappiness is proportional to how much these summaries disagree. And there are actually a lot of ways to keep those summaries small when a subset of nodes agree. And I'm not going to get into that in too much detail, but the magnitude of divergence here is really the amount unhappy it is. The more mutations need to be sent back and forth, the more expensive it is. But typically, especially if we're running this as part of, we're running reconciliation constantly, this should be very few mutations. And another important thing to note is that when these mutations are sent between nodes, even as part of re-reconciliation, that can mark them as reconciled. So then nodes know that they have what they were missing, and those new mutations, even if they were received during a read, count as reconciled, and so the reconciliation state progresses. This is in contrast to read repair, where the mutations that come through on read repair end up making the unrepaired set bigger. They come in as fresh mutations and still need to be incrementally repaired in order to pay that cost down. So in this case, we are actually doing reconciliation during a read, and after a read, we will no longer need to look at that data for anti-entropy purposes. The other unhappy path is if we have a really extended outage and summaries end up being really big. So imagine there's a node 3 that's been AWOL for a month, has not shown up, and is still considered a replica, a node down in the ring. The other replicas can't mark any of that data as reconciled because node 3 hasn't received it. And so their summaries will grow. They'll have more and more mutations where they have to track their IDs and need to keep those IDs until reconciliation happens. And this is relevant for longer term extended outages. But there are a number of really good techniques we can do here too. One of them is if a node is down for a long time, it should probably be replaced at a certain point. So host replacement should account for synchronizing nodes that may have been down for a longer period. But we have a few other techniques in mind where if two nodes are in sync, like in this case, nodes 1 and 2 have been healthy for the last month, we don't necessarily need to include all the unreconciled mutations that node 3 doesn't have. So we can even keep the unreconciled set, this sort of pairwise unreconciled set, even smaller, even if one node has been down for a long time. But recovery for extended outages is still an area that we're focusing on just to make sure it doesn't put a cluster into a degraded state. So to recap, this is a really precise, continuous reconciliation of individual mutations. So it permits larger values, permits larger partitions. We get really fast reconciliation planning. So when we're figuring out who's missing what, we can do that really effectively without going to disk or producing digests. We also get consistent reads with way fewer disk accesses and way less data sent over the network. So at RF3, we only need to do 1 data read instead of 2, and for higher RFs, the savings are even greater. We also don't need to do anti-compaction. So we don't need to separate out SS tables that are participating in repair. We don't need to do any excess flushing because we don't need to flush in order to repair data. We don't need to produce any digests of user data that's on disk, so we don't need to pull it off disk, and then we don't need to come up with a digest. We don't need to deal with digest false positives either, because we're giving a compressed representation, a lossless representation of a bunch of mutation IDs, as opposed to a hash of a set of them, which can only be comparative. You only get meaning if they're equal. Really. And we have no overstreaming, because we can send individual mutations that are missing instead of not being able to stream any less than a whole partition. So we get a lot of perks out of this kind of tracking, both on the read path and on the write and reconciliation paths. And yeah, we're really excited about it. But this is a pretty big change. Read and write paths and anti-entropy, they're all closely related to each other. So there's a lot in here that I didn't cover in as much detail. I didn't talk as much about the improved guarantees that I mentioned. So write atomicity and read monotonicity, or short reads, there's a whole gamut of read corner cases that this supports much better, but are more detailed topics. I also didn't cover compatibility with Accord, or SAI, or CDC, or analytics, which are all included in the design, but could be talks in their own right. We're intending to support migration of existing tables. That continues to be in progress. And then the other one that I mentioned earlier, of validation repair. So the detection of reconciliation violations, which right now is really necessary for finding these logical bugs. There are some really interesting things that we can do with IDs, because we can fetch the contents for those mutations. And we think that we can actually do much better in terms of continuous invariant checking for violations. But this is still an area that we need to prove out some more. So that's everything that I'm covering. Also really want to encourage everyone to come to Scott's talk tomorrow. I'm sure you are all planning to. But it builds upon the foundation in mutation tracking, talks more about what witnesses are and how those can reduce costs even further. So yeah, that's everything. And now I will go to questions. Well, I feel I should switch.
It seems like a really well thought through kind of, I'm just kind of, the scope of what you're attempting in this aspirational thing that you're doing is like, it's kind of an enriched headed handoff, an enriched read repair, and going across replicas, which I was trying to get to there as well. But is this replacing all of those subsystems for anti-entropy, or is this augmenting some of them to say, because I saw the incremental and things like that, is this also going to, so this seems like it'll replace hinted handoff and read repair and more effectively, but how does it interact? So are you replacing all anti-entropy systems with this kind of universal real-time anti-entropy?
So the parts that are certain are hints, replaced,
Yeah.
and read repair replaced. The relationship with incremental repair really depends on the migration flows that we need to support, because they are very different paths, and we need to make sure that we're not. One important part of mutation tracking is that we can't introduce data without giving it IDs. We need unreconciled data to have an ID so that we can mark the presence of it and the propagation of it. So the intersection between mutation tracking and full repair and incremental repair would require changes that could make things far more complicated than they're worth. So the direction that we're hoping for is to no longer need full repair or incremental repair in this world, but the specifics of that and making sure we can do things like it's great when you can run both for a while. It's part of the migration.
That's what I was wondering. Is if it's like for now, it's like you can get rid of and improve and everything on headed handoff and read repair, and then later it could be that it takes over the other role as well.
Yes, I think the intent is to not need them anymore, but we still need to figure out what the transition looks like, because removing support, replacing 4 things is risky, but also requires a lot of thought, making sure that we're not making everything more complicated in the interim states too. Chris.
I have a lot of questions, so I'll probably just pull you for later.
Okay.
Just a quick glossary thing with the ID summary. Is that the mutation IDs for a specific ID, key? Is that what you meant by the ID summary, as opposed to the?
Yes. So you can have you can get the unreconciled. Summary refers to just a set of IDs, basically. But when we're fetching summaries as part of reconciliation, that is the unreconciled IDs for either for the read, so for a token, or for a range.
So it would be.
It'll be scoped, yeah.
Okay. Then another question, sorry, quick, is if we have this, would that mean that when we're doing things like bootstrapping and for to needing the repair for replace and stuff like that, would it just be able to pull from both replicas, get those mutations, and then be no more need for repair for replace, and we're good to go? Is that kind of
that's the intent, but that's still in progress. So the intent is to the current state of repair for replace is it's a lost rights gap. Not doing it is a risk, and so we intend to have bootstrap be correct from the beginning. No, Scott. I
was curious about. It seems like you're swapping memory or disk for memory. What's the impact on memory? And does this require is it better to is 21 Java 21 and above, or using things like SIMD? It seems like there's a whole new memory requirement that's going to be put on
the memory requirement is a lot less than it seems, because the part that's in memory is just ints.
Yeah.
So instead of a mutation being however big it is, it's an int, and adjacent ones are represented really compactly. So
it's sorted and okay.
Yeah, and we don't. If I go back to the, we will have very few host IDs. We'll have very few log IDs. It's mostly sequence IDs, which we have 1 of per mutation, and then the timestamps are optional and actually fall off at some point. So
yeah, I'm thinking under high load, sequence IDs there's gonna be a lot.
Yes, but we also don't need. There's a lot of work that we don't need to do anymore. That will also save on memory. So the intent is that this is actually much lower overhead than current paths, even memory dumped paths. Is not.
Oh, yeah, I was just gonna say that I think that within a log ID, I have at least a month worth of sequence IDs even under it's there's a lot of numbers in that that you fit into.
Anything else? Oh yeah, stop.
How about tombstones? So if tombstones are reconciled continuously and immediately, do they become purgeable immediately as well, so long as the data they shadow is also compacted away?
So there is potential, I think, for a more sophisticated tombstone purging policy. based on this. The safer and easier thing to do though is to do only purge repaired tombstones, because we can actually, in this case, flush a mem table directly into the repaired set. So we flush a mem table, it's immediately repaired, and then with OPRT, we're only purging repaired tombstones, and we don't need GC Grace. So
Maybe.
Yeah.
sorry.
Very the lead.
On the next slide, I think you talk about the mutation log, or maybe it's two back now. Is that a separate?
This one?
Sorry, the mutation journal.
Yes.
Is that a separate item on disk,
That,
or is that an enrichment of what we already have in the commit logs? Like you enrich commit log with the IDs.
so the mutation journal is supersedes the commit log and is intended to be compatible with the commit log. This is also a requirement for Accord. Having the mutation journal.
It's one of the Accord data structures that is now being used by Mutation
Yep.
Tracking. Is that right?
So there are multiple users of this new indexed commit log, addressable commit log functionality. It won't just be this. But yes, this supersedes the commit log. Yes, Andy.
Question. So I was trying to think about hints. Like one of the problems with hints is they can accumulate and take up space on disk, and then we have the hinted handoff window where we can start getting rid of old hints. Like, is there any concern about, like, you kind of mentioned a node being down for a long time? Is that going to cause things to accumulate, or will that not have a?
Yeah, so if a node is down for a really long time, then the life cycle of the mutation journal, it's a commit log, but it has a different life cycle from the commit log. The commit log we can reclaim segments from when we reach durability. So when we get a flush, we can say we no longer need this in the commit log. For the mutation journal, the life cycle is extended because we need rows in the mutation journal for as long as we might need to look them up by ID, and we need to look them up by ID as long as they're unreconciled. So instead of just being durability, it's reconciliation state, and we intend for reconciliation to keep up really, really closely because it's running continuously. But if a node is down for a month and reconciliation can't happen, that is the main recovery path that may be slightly different, where we will want to truncate from the mutation journal. So we have other strategies for that.
Gotcha. So it's really important to not have nodes down for a very, very long time, then, right? So,
But that period we intend to be really long.
Yeah.
And is also dependent on the right volume. So it is theoretically, there is theoretically an accumulation. I mean, there's potential for this to take up more space on disk, but there are a lot of ways also to basically purge it out of the mutation journal into SS tables and then ship those SS tables on recovery.
Gotcha.
So that way we wouldn't be taking up the duplicate space. So we have a few different approaches. Chris, did you also raise your hand?
No, yeah, I'll let other people ask questions first.
I think other people don't have questions.
Well,
unless
after.
You go first. I already asked you too. I just had to think.
Okay, so when you say that there's no GC Grace, and yet we're still recording tombstones, where, like, then you're storing them for how long then, I guess?
so. When I say no GC Grace, I actually don't mean any changes in that area. So even with GC Grace, with only purge repaired tombstones, we only purge tombstones out of compactions within the repaired set. So with that flag enabled, we wouldn't have data resurrection issues.
So if a tombstone is in the repaired set, then you can purge that from a compaction following it being in a purge set, rather than waiting for the GC Grace and then waiting for a compaction and then purging it.
Yes.
Right?
Yeah.
The life cycle.
Yeah, if it's in the repaired set, it's safe to purge. So every compaction that is in the repaired set could decide to purge tombstones, and we just prevent any tombstone purging in the unrepaired set. That's kind of the simplest solution because we're already updating SS table repaired state based on the reconciliation state. So if all of the mutations in an SS table are reconciled, that SS table is repaired in the same way that incremental repair would mark it. But this could mark an SS table repaired on flush.
Right. But coordinating across replicas though means that you're guaranteed to have that tombstone when it's in that repaired state. Like all replicas will have that same awareness of that repaired state.
All replicas will know that mutation is present everywhere. There could be a lag, for example, where a tombstone isn't purged on one replica because it isn't aware yet that that mutation is reconciled. Like there could be
Okay.
one node
That's,
could be
that's,
aware of that.
the
but
global state is all the thing that I'm most fuzzy about right now. Because saying like, okay, I'm a coordinator, I have hints, but I only know about my hints. But in this case, somehow you're globally
So that's a part
propagating that state.
that state of which basically the reconciliation state of peers is also shared, but maybe stale. So peers will broadcast their reconciliation state to others, and so a node will know, even if it wasn't involved in reconciliation, it will find out that a mutation is reconciled because someone else has applied it finally.
Interesting. Okay.
So that is still propagated. That's like a
I'm paranoid a little bit, but yeah, it'll be interesting to see the full life cycle of everything a little bit better.
yes.
If the mutation journal gets corrupted for any reason, like we have to rebootstrap the node from scratch.
So it supports checksums and encryption, but it would be the same as a commit log corruption, where you basically have to treat it as a host replacement. Or you could replay the commit log and
You can run repair maybe as well. Like it doesn't guarantee that you won't have inconsistencies.
yeah, we can also do a rebuild. And it would be
So you have ways of rebuilding the mutation journal. You should.
You wouldn't. In that case, I don't think you would need to. You would, yeah. We need to, for unreconciled mutations, during a host replacement, for example, we do need to make sure that unreconciled mutations have the appropriate state attached. Like we don't want to send a mutation as part of a host replacement that is interpreted as being reconciled if it isn't. Because then that would impact purge behavior and things like that. So we do need to attach some of the reconciliation state when we do things like rebuild.
Yeah, I don't think it's actually safe to repair when you have a commit log that's been lost. Just
Yeah, you have to treat it as corrupted.
Yeah.
And replace them.
So
Yes, sir.
Do you have another, or Chris, were you done?
I have one.
No. I kind of entered I just kind of kept going, and then I finished way sooner than I planned to. So keep it up.
You listed on the thing that the sequence ID was an integer. Is it an int or is it a long? Is an int going to have issues with overflowing or anything?
So there is a world where host ID is fixed, log ID overflows. So these are all ints. We roll over a log ID.
Also,
When
log
it's
ID will increment with
Yeah.
sequence ID.
And so there is a room for wraparound that we do need to make sure is addressed, where the log ID also wraps around. But that would take a long. We need to do the napkin math on how long that would take.
Yeah, with the sequence ID I could totally see.
Yeah. But when sequence ID is full, log ID bumps.
Okay. That makes sense.
And so it's on restart for this crash safety, and it's also when we run out of space in the log ID that we run that out.
You mentioned reconciliation a lot. Is there a who does the reconciliation, and then who, like, is there coordination amongst which the replicas will do the reconciliation? Like, will they ever run at the same time? Will there be?
So a coordinator, it's a coordinator will reconcile its the mutations that it has coordinated, and peers will share their reconciliation state and request things that they are missing.
So if a node crashes, though, it loses it. So then a replacement node has to, like, when a coordinator goes down, though, something else has to reconcile.
Nodes that are missing it will request it. If the coordinator is down and they cannot fetch it from the coordinator, they will know what they are missing because the sequence IDs are broadcast. Who has what is broadcast. And so a node will find out that it's missing something, try to get it from the coordinator, and if it can't get it from the coordinator, it'll get it from someone else who's known to have it. So the state of who has what in ID space is broadcast periodically.
Yeah, I'm wondering more about in lines of to like, you have this huge set of mutations, the coordinator goes down, new node comes up. How do you like choose then who is the one who's going to coordinate that reconciliation between those large sets of mutations?
So everyone will be doing their broadcast of what they have.
So it's like a continual
Yeah.
thing.
And so even if a coordinator goes down and cannot actively coordinate like its failed writes, for example, which it can do, like a coordinator has a little bit of extra knowledge and that it can try to broadcast. It knows what of its writes have failed. But if in the absence of that, in the background, nodes will be broadcasting which IDs they have. A node will find out that it's missing an ID as part of that broadcast, and it will fetch it.
Okay.
From whoever it knows has it. So it's
So where does that broadcast happen? Is that in
Yeah.
ASA or
no, it's like a separate internode.
Is that a part of the repair, like the table will be repaired similar to transfer V2?
Sorry, I didn't fully do it.
Will those IDs be kind of propagated to other replicas through repair mechanism like Plexus V2 has like 5 minutes?
Not through that, through its own periodic broadcast.
So there's no messaging.
It's its own messaging. I mean, you know.
All right.
I'll talk to you.